Hello, everyone. My name is Saurabh. I'm the tech lead for the machine learning platform team at Pinterest. And today with me is also presenting Raymond, who is a senior engineer on the ML training team. And together we are here to present some of our recent work on distributed data loading with Ray for recommender model training. So just to give a little bit of context, this is what the primary Pinterest product surfaces look like. We basically have home feed, where we recommend content to you based on your interests and past engagements. We have related pins, where we recommend content similar to you based on the content that you're currently interacting with. Then we also have the traditional shopping surfaces, where you can click on different objects that are in the images and you can shop them. And then we also have the traditional text-based search surfaces. And the reason why I'm mentioning all of this is because this is all powered by hundreds of different machine learning applications that is running on thousands of GPUs in real time on web scale data. So all of this is actually a very massive scale machine learning problem. And today, amongst all the different ML applications that you see here, including recommendation systems, graph machine learning, and so on, we'll be particularly narrowing down and focusing on the recommender model training. And the reason for that is, like in all the Gen AI discussions that are happening in the industry, recommender models are still the bread and butter for many different companies in this space. And they underscore some of our critical product surfaces, such as home feed and related pins. And they're also the key drivers of our performance-based ads businesses. And so any improvements in this recommendation model training can directly impact our product. And just for anybody who is not familiar, to define the problem formulation, you can think of the main problem that we are trying to solve is what is the probability that the user will perform an action given some context about the user, the item that we are interacting with, and some other features. Based on the description, I think you can imagine that most of the training data sets are some form of engagement logs. So they are highly structured data, and they are typically in a tabular format. And most of the inference happens in real time at very low latencies. So we'll start narrowing down a little bit, and I'll first speak about the training setup itself. So this is what our typical training setup looks like. We have a shared unified training compute platform, which we refer to as TCP. As you can see in the diagram, both the user-submitted jobs and our scheduled workflow jobs all are backed by the same shared job submission API. And all of our workloads are directly orchestrated on top of Kubernetes, which is running in AWS Cloud. And we have a variety of different GPU types that we use. The framework of our choice is PyTorch. We are predominantly on PyTorch now, and we use a thin wrapper around PyTorch, which we refer to as MLenv. And as you may have already guessed, most of our training data sets are tabular ML, so we use Apache Parquet heavily, and they are backed by Hive and Iceberg both. So just to give you a context of the scale of the jobs that we run, typical training jobs that we have use anywhere from like 8 to 16 A100 or H100 GPUs. They can run anywhere from 20 hours to 300 hours, depending on the use case. But the most interesting part here is the scale of the data sets that we use. A single training job can consume hundreds of terabytes of data that spans across like 100,000 or more files. So this is actually a very large data set. And the whole target of the talk today is going to be the GPU training pipeline. And what I mean by the GPU training pipeline is, if we imagine the whole training setup, the goal is to stream mini batches of training examples as fast as we can throughout this pipeline and get them to the model. And the idea behind this optimization is we want to drive up the training throughput in terms of the number of examples per second that we process, which naturally drives down the job runtime and the job cost. What you can see in this diagram is there is a section that I've highlighted in dark gray that represents the data loader or the plumbing code that gets the data to the model. And you can see that the bottom right, there are only two steps that the model actually represents, which is the forward and the backward. And so it's a very small piece of this whole execution pipeline. Within the data loader itself, you can see that I've highlighted different components in different colors. The yellow parts are typically the CPU preprocessing parts. The green parts are memory operations. And the purple parts are what is actually executing on the GPU. So if you look at the typical pipeline, the way it looks like is you perform some kind of a file I/O, read from Parquet or some other object store that you have. You have one or more user-defined functions that you execute after that. So these can be any Python-based conversion functions that you have. And then you have a tensor conversion step where you convert all of this data into your framework native format. And that's when you enter the memory operations where you perform, say, copying into pinned memory. And from pinned memory, you move it into GPU memory. And then you perform some operations in the GPU, and finally you yield that batch to the model. So the target of the optimization is going to be everything in the gray box, and it is important for us, and here is why. So the target use case that we are going to look at is our home feed ranking. So this is a pretty important use case for us. This is the use case that recommends valid content to the users on our home feed. And when we started this whole optimization work, the throughput that we were observing for our models were like about 80,000 examples per second. And we knew that there is an abundant headroom that we can squeeze out. And so we started just exploring what are the possible bottlenecks that could be hampering our progress. And here I've just listed a couple of them. So like as you can imagine, the most obvious bottleneck could be the model itself, where you are just purely GPU compute bound, and that's that. The other one could be that you are actually bottlenecked on the memory operations, where when you copy from CPU to GPU, you have some bottlenecks like PCI bandwidth. You could also end up having CPU pre-processing bottlenecks, where you have so many inefficient pre-processing operations that is hampering your throughput, or you could be purely file IO bound. And I've just tried to like illustrate this in the code example. Like this is what a typical training setup looks like. The first line that you see is you instantiate a model, then you construct some form of a data set. This is where you configure the file IO. Then you pass that data set to some form of a data loader, where you pass a collate function. And the collate function here is the one that is responsible for applying all the CPU pre-processing before your model gets the batch. So this is where the CPU pre-processing is expressed. And then you have a traditional training loop where you iterate over the batches from that data loader. And then the first step that you do is you copy that batch into the GPU, which is the call that you see for send to device. And then there are the 3 standard steps in any model training, which is the forward, backward, and the optimizer step. So to understand where the bottleneck is coming from, what we did is we tried to eliminate one bottleneck at a time. And so we first tried to understand if model itself is our bottleneck. And to assess this, what we did is, if you see the gray line that I've drawn, we basically froze a batch. And what I mean by that is, after the data loader produced the first batch, we just froze it on the GPU, and then we just like constantly looped over that same batch, effectively disabling the data loader after the first batch is prepared. And to our surprise, what we saw is like, if you see at the bottom, after the batch is frozen, the throughput jumps to like 500,000 examples per second. And what we were actually observing in our real workload was just 80,000 examples per second. So there is like a 6x-ish headroom that we had to actually optimize and squeeze out the most performance. And what this effectively meant is that the time it took for the model to run is a lot smaller than the whole training iteration. So we knew that we had something to play with here. And we just tried to reason about why this could be happening. And I think it's fairly intuitive as well. One of the most important reasons is like, these recommender models are actually served at very low latencies because of the product needs. And so they are typically a lot smaller than the generative AI counterparts that you see. And so they end up having a lot less compute compared to the Gen AI counterparts. The other thing that makes these models very tricky is they are highly data intensive, meaning that their data to compute ratio is a lot higher. And the reason for that is like typically these models use hundreds or thousands of features. They have very large sequence features that they use, and so it becomes like very memory and data heavy operation. And the thing that like makes this a little worse is cloud instances typically come with like fixed CPU to GPU ratios, and so you cannot arbitrarily scale up the CPU pre-processing parts. So this is the bottleneck that we were trying to address. And before going into any advanced solutions, the obvious thing to do was to just reduce the amount of data that we are processing. And so the first obvious thing that we did is, let's just target the most expensive features that we have. And so what we ended up doing is we started leveraging sparse tensors. And the idea here is, if you have a large number of sequence features, which can be mostly empty, we basically just skip storing all the empty slots. For this, we started using tort sparse CSR tensor format. And the idea here is, before the model consumes it, you actually densify the tensor back on the GPU. And the reason why this is highly effective is, even though you still end up densifying, it has some implications on 2 fronts. Like the first effect that you see there is the data compression. Because you use sparse formats to represent the data, the amount of data that you store on your bucket storage is a lot less. When you perform any kind of file IO and you pull down those bytes to the actual training node, you perform a lot less file IO compared to before. And so both of those steps are optimized. The other interesting effect here is the data movement, where those bytes that you are trying to carry forward from the bucket storage to the CPU pre-processing steps across the PCI bandwidth is a lot less. And so in the diagram, this is just pseudo diagram, but like what you can understand is before, if you're trying to transfer a lot more bytes, you can see that the host to device transfer can be a lot larger. And what we are trying to do later is transfer a lot fewer bytes, but then densify it within the GPU. The reason why the second is faster is because GPU has a lot more memory bandwidth. So even if you end up doing more work, the second step is actually a lot faster. And what we saw is because our data sets are dominated by these sequence features, you can see that when we started using sparse tensor formats, our throughput jumped to almost 2x of what it was before. So we knew that we are making progress in the right direction. Like just making this one change brought our throughput to like 160,000 examples per second, which is 100% improvement. So we just decided to double down on this approach. The thing that we did next was we tried to use application-specific optimizations where we knew that given that we have Parquet data sets that we have, if we sort the records in the correct order, Parquet can perform a lot better job of compressing these data sets. And so like effectively reducing the amount of bytes that we have been using to power these machine learning use cases. And so like all we did is just sort the data in the right order. And the effect of this is again the same thing that I described before, which is it compresses the data on storage and it minimizes the amount of bytes you transfer over the file I/O. Again, this change multiplied and like gave us compounding effects on the previous change. And you see that the throughput now increases another 30%. So we are already at 260,000 examples per second. Like we went from 80 to 160 to 260. But here is where we kind of hit a wall, where we knew that we are about 260,000 examples per second. But based on the benchmarking that we did, we know that the headroom is like 500,000 examples per second. So there is like abundant headroom that we can still leverage. And the observations that we had were that like still we were very data and CPU pre-processing bound. And we were to a large extent also file I/O bound. And what we had to do is instead of just shrinking the data, we had to figure out a way where we can scale out the data pre-processing itself. And we had to break out of this like fixed CPU to GPU ratios that we had available on our GPU nodes. And so that's what we ended up doing next. So as you may guess, Ray was actually a good fit for us to solve this specific challenge, and that's why we adopted Ray. Particularly, like two properties were of interest to us. One is Ray core is actually a distributed heterogeneous CPU-GPU runtime, which is exactly what we needed. We didn't just need GPU nodes. We wanted abundant CPU nodes to power the GPU nodes as well. And given that now the training job is going to be distributed in its nature, you also need like good UI and debugging tools, which Ray core provides out of the box. And the Ray ML ecosystem was also of interest to us, particularly Ray data, because it allows you to express last mile data pre-processing. So what we set out to build is actually what we refer to as the distributed data loader with Ray. And the idea here is simple. We basically want to increase or scale out the number of data loading workers that you have for every GPU trainer. And the way we do this is by adding like 3 or more CPU nodes into the mix. So as you can see in the diagram here, we have like all of this is running on Ray. The dark gray ones are pure CPU nodes, and they are doing the job of data loading, which is basically file I/O and any CPU pre-processing. And then these mini patches are transferred over the network into the GPU node, and then the GPU node is just running the training loop. So as I described before, like all of the file I/O and CPU pre-processing is on the CPU nodes, and the batches are transferred over. And this is also where we introduced Ray data as a means to express map batches, where we can apply like any filtering, downsampling of the data sets as a last mile transform. So when we actually developed this and tried to run a job with this, the expectation was that this will help us bump the throughput up from like our current throughput of like 260 to somewhere close to 500,000 examples per second. But this is what actually happened. So we added 3 CPU nodes into the mix, and we expected the throughput to be somewhere between 250 and 500. But the actual throughput we observed was just 110, which is lower than the single node throughput that we have. So it's clear that just adding CPU nodes was not the solution. And when we tried to figure out what went wrong, there were a few things that we saw. First is that because of the way Ray data and Ray data iterators are set up, the expensive CPU pre-processing parts, at least some of them, are still happening on the GPU nodes, which is not what we wanted. The second is, because of the volume of the data that our model needs, the Ray object store transfers itself started becoming a bottleneck. And the third thing is, because Ray data is a general purpose data pre-processing system, it was lacking some of the critical data transfer components that machine learning models need, like GPU preloading, memory pinning. And so that's what we ended up doing. And I think Raymond can continue the rest of the story.
So yeah, hello everybody, I'm Raymond. I'm a senior engineer in Pinterest ML training infras. So I'm going to continue talking about the journey we applying Ray to train Pinterest home feed rankers, and then also the optimization we done to further improve the data loading bottlenecks problems. So before we dive into the details of the optimization we have made, let's first take a look at the initial setup of our architecture of the trainings. Right? So the initial setup is actually follow a typical Ray data plus Ray trains architectures. So we first have a Ray data pipelines to do data loadings on the CPU nodes. It is responsible for IOs and also user-defined transformations. So once data is being prepared, then string back to the individual training process through Ray data streamings, and then going through a few final data processings, preparing the batch, then finally sending to GPU memory for compute. So now the first challenge we were facing here, as you might already seen here in the diagram, is that we still have some like expensive CPU processing, right? So the first thing we discover is this batch formation living inside the Ray data iterators is very expensive because this needs a full data copying. So, and then since it's done in a GPU process together, that frequently cuts GPU idle times. And then furthermore, it's not allowing us to scale this operation efficiently without touching the GPU resource. They have to scale together, which is not what we want. We want to scale CPU operation independently. So then the obvious thing we are doing is just moving these operations into upstream pipelines. So that what we do is to implement batching as an actors, and then being able to run this operation in Ray data pipelines. So by offloading these CPU-intensive operations, we are actually being able to reduce the GPU idle wait times. And then furthermore, this operation can naturally scale with as part of the Ray data pipelines scaling. So now the next bottleneck we are facing here is the slow object store transfer. We discovered that no matter how much we scale the CPU nodes, it's always bottleneck from certain numbers. And then this is due to a variety of problems, but mainly because the data compressions between CPU and GPU node. So in S3, we usually save the data set into a ZSDD compressed format. And then this is also the data format we going to transfer the data from S3 to CPU because it will reduce the I/O cost. And also with the ID sorted dataset we mentioned before, this dataset is usually very highly compressed. But once the CPU node read and process the data and trying to send them to GPU node, we found that this living in uncompressed format because by default, object store doesn't provide any of the compression method. So now a lot more bytes have to be sent from CPU to GPU, and then this causing a lot of severe bottlenecks here. So now the idea is to also apply a ZSDT compression, right? So that we don't have this severe number of data need to be transferred. So we just applying a custom patch to the Ray core object store layer in our open source fork, so that every data object have to transfer between Ray cluster, between nodes. They are also going to be ZSDT compressed. So then the observation we have here is that now the compression ratio between for the data sending from CPU to GPU is actually matching the compression ratio we have in S3. And ultimately, it reduces more than 10 times of the number of bytes we have to be transferred, and then relieve this as the bottleneck in the applications. So now we solve the object store bottlenecks. Then that's looking back to the overall pipeline again. And then we still see that there's some other CPU operation as well living inside the GPU process, which is specifically this is collate, where we're trying to convert the pi-arrow table into the dictionary tensor. And this is especially expensive, combining the fact that we have complex features like sparse and rag tensor living in our batch, so that it now still introduce some overhead, right? So borrowing from the previous learning, we also want to move this collate out and then move into the dataset pipeline so that it won't cause GPU idle times and then can scale. But then the other challenge we face here is that the output of the pipeline now become a dictionary of tensor, which is not super friendly at this point with rate data interface, especially we have this special reg tensor and sparse tensor specific to the PyTorch training worlds. And then while dealing with this bottleneck, we also, in the same time, discover another kind of overhead during the entire data movement funnels, right? Meaning when we're moving data from remote CPU memory all the way to GPU memory. This overhead typically scales as number of feature columns grows. For example, in this diagram, we also shows the screenshot of the trace to take a data out from object store. And then in this example, we found that for each of the feature columns in the batch, we have to pay a small amount of unpickling overhead to take them out. This might be fine for some usual cases, but for Pinterest, because a model consumes hundreds or even thousands of the features as an input, so this overhead quickly become non-trivials. And then as a comparison, we list the forward pass here. You can see that this unpickling overhead itself is already 1.5 times of the forward pass, so it becomes another bottleneck we want to solve. So now, in order to deal with these two problems together, we introduce a custom serialized batch format where we try to put all of the tensor binaries into a single contiguous buffer, so that this operations is done in the CPU nodes once we finalize the preparation of a batch, send them all the way to the GPU nodes, and then finally only unpacks after we are ready to move them to GPU memories. So the first effect of this is now the serialized batch is now can further fit into the rate data interface patterns, and then help us to move the collate this expensive the final expensive operations out from GPU process. The second effect is around the fix of this data movement funnel overhead. Now we can reduce this ON overhead to actually just O1, because we now effectively only transfer one columns. So for example, the pickling overhead have drastically dropped from more than 400 milliseconds to just sub 20 milliseconds. Right, we talk about all of these, all of the three challenges here. Then the final challenge is just the missing data movement components that we currently have in the Torch data loader infra, but it's missing in the current rate settings. So in the left diagram, it shows like how are the GPU process implement this pipelining to move the data directly to the GPU memory. So the first thing we are missing here is this pin memory stage where in Torch data loader, when the GPU process receives a batch of data, it offers the functionality to move them to pin memory as well. The pin memory is referred to a non-pageable memory in OS, but the TLDR is that it helps us to speed up the GPU memory copy in a later stage. So the second stage missing here is that in our previous setup, we also introduced an additional pipeline stage where we try to use another CPU thread plus the side quota streams to preload a batch ahead of time before the next model compute executions. So this effect is that once the model finishes the current computations, you can immediately start the second one without waiting for moving the batch it needed to GPU memory. It is already preloaded there when you want to start the computations. So yeah, so the final thing we have to do is to add these two pipeline stage into our array training setups in order to fit in more into the ML training ecosystem, and then make sure that we can offer that as much as possible, the non-compute overhead with the GPU compute itself. So finally, after we apply all of this optimization with the same compute setup, 1P4D plus our 3R7i, we can actually reach a pretty good throughput of 400K per second. It is like 3.6 times more than what we initially have in the initial RAID setup. It is also still 50% more performance from our original torch data loader setup with sparse tensor and ID sorted data sets applied. Now, in our also latest experiment, we see a good scalability as well. When we're performing complex row sequence feature processing, we are also able to scale the CPU machine up to 32 nodes in order to achieve the same throughput number here. So some of the general learning here is Rex's models in Pinterest really moving toward data-intensive world where we try to consume larger and larger row sequence features, adding more complex in-trainer data processing in order to do experiment faster. So we really need this very heterogeneous cluster in order to break out the fixed CPU to GPU resource constraint. But now efficiency of the training is still a complex problem. It not only needs GPU compute to be fast, but also data loading and even the data movement funnels to be performant. Some of the useful tip we discover is that we want to reduce the physical bytes needed to be transferred across the entire funnels. For all of the CPU operation, we want to move most of them as much as possible out from the GPU process into the pipeline itself. And for those critical paths that we cannot move, we want to make sure it offer that to GPU compute as much as possible so that minimize the overhead coming from this data movement. And then finally, really provide this really good scalabilities, and also in the same time, it's flexible for us to customize any optimization we want to fit in our own ML training systems. Cool. Finally, just want to mention that this work cannot be done just by two of us. And then this is actually a lot more work done by multiple engineers in ML training, in Pinterest, ML platform, and ML engineers, also any skill engineer as well. So just want to give a quick acknowledge and shout out to them to make this work happen. Yeah, let's conclude our talk.